BITS Goa would like to invite Professor Eric. Now, before Sir proceeds to start the lecture, I would like to give a brief introduction about him. Professor Eric, a PhD in physical chemistry from the Department of Chemistry at Harvard University, is now a Commonwealth Professor in the Departments of Chemistry and Astronomy at the University of Virginia. Our professor has won a number of international prizes, one of them being the Centenary Award of the Royal Society of Chemistry. Now we come to today's lecture, Astrochemistry, now and then, the current state of the subject and its amazing development. Over to you, sir.
Okay, well, thank you very much for that nice introduction. Normally, what we do is we use the second name, the last name, so you would say Professor Herbst, but I guess Professor Eric is fine as well. Okay, the title of my talk, Astrochemistry Now and Then, the current state of the subject and its amazing development. First, a few words on what is astrochemistry. It's very similar to astrophysics, and what astrophysics is using the techniques of physics to understand things that happen in the universe. Then astrochemistry is a newer subject in which we use the laws and rules of chemistry to learn about what is happening in the universe. Now, to be more detailed, all right, how do we...
You should be able to click on maybe just the screen.
Yeah, with this.
Yeah, and now try it.
We can do it. Okay, fine. So, thank you. My student here was helping me. All right, so a more detailed view of what is astrochemistry, some of the things you do with it. Number one, it's the study of chemical reactions outside of the Earth and the solar system. So we're going to study what happens in chemistry throughout much of the universe, actually mostly in our own galaxy, the so-called Milky Way. Next is we use telescopes with spectrometers. Now, telescopes are used to get enough light from space so we can see something. Spectrometers, depending on whether they work in the radio or in the visible, they separate the light or the radio waves into different frequencies. And the frequencies are what tell us what molecules are emitting or absorbing radiation from space. Okay, so we can find molecules throughout the universe. Finally, the role of molecules in understanding the birth, life, and death of stars and matter in between stars. This is called the interstellar medium, and it consists mainly of clouds. And I have a very nice picture. Okay, this picture is of some clouds, and as you can see, okay, I'm trying to get the cursor here, but I don't seem to be succeeding. All right, so if we are let's try again. No. All right. So what you're seeing is a picture of the Milky Way. That's very bright stars towards the center of the galaxy, and much of the light is blocked out by this dark stuff. The dark stuff is called a cloud, and it's a particularly dense cloud. It consists of gas and dust, and it's in front of the visible light. So if you're trying to look for spectroscopy in the visible, that is shining visible light and something and seeing what it does to it, you can't really do it here because the dust and gas in these clouds actually blocks much of the background light. It does turn out, as we'll see later, that if we actually study these black objects, that we can study them at longer wavelengths than the visible, because infrared waves and microwaves actually can penetrate through these dark regions. Now, these clouds of gas and dust come in different densities and temperatures and with different chemical processes. So from chemical processes, we can learn a lot about these clouds. Okay. So let's look a little at the spectroscopy. And to make life simple, we're just looking at one diatomic molecule. And this diatomic molecule, there are many molecules in these clouds, much bigger than diatomic ones, but this is a good picture, I think. It shows the three types of spectroscopy that astronomers or astrochemists use. And this diatomic molecule is rotating and is vibrating, and in addition, electrons are moving around the diatomic molecule. So these motions, I show here lead to absorption or emission of radiation. So a molecule can emit radiation, and if there's some background radiation behind it, it can absorb it. So you can see absorption or emission. So rotation, what happens if a molecule rotates, you see radio waves. Radio waves are very important and are seen with radio telescopes. And radio telescopes give us, just like a radio gives frequencies, the radio telescopes tell us the frequencies of molecules. And from that, we can actually get the structure of molecules. The next type of spectroscopy, which has bigger frequencies, that's why it's a bigger arrow, is in vibrational motion, and what we see then in absorption or emission is in the infrared. The eye can't see in the infrared. The infrared has more trouble reaching the Earth than the radio because of all the water vapor in the Earth's atmosphere. So most of what we will be talking about has to do with radio waves. Okay. Finally, the highest frequency or the shortest wavelength of UV or visible radiation, we call that electronic radiation because it happens because the electrons are moving. And that can be done if you have, say, for example, a background source in the visible, and it shines through some object that's partially transparent, then we can get electronic spectra. And I'll show you examples of all of these. All right, so instead of looking at all of these clouds, here what we're going to look at is an individual dark cloud. It's in the constellation Taurus, and it's called a cold core. Now, if you take a look at the background here, you see a lot of black stuff, and it looks like it's nothing, but it's not nothing. It's just dust and gas blocking background radiation. Okay, so. But it blocks it mostly in the visible. We can see some in the infrared and a lot in the radio that actually makes it through to us. And so we can learn from this that there are molecules in the gas and molecules on the surfaces of dust particles. The most abundant molecules in the gas are molecular hydrogen, that's H2, and carbon monoxide, that's CO. But there are many other exotic molecules, as we'll see. The temperature of this region is 10 Kelvin, so that's quite cold. The density in the CGS unit system is 10,000 molecules per cubic centimeter in the gas. I used to say that was a spectacularly good vacuum, and that it was less density than anything we could make on Earth. I'm told that's no longer true. You could make a better vacuum in the laboratory than you can in space, but still it's not very dense. So the gas phase here, the molecules don't collide very frequently, unlike what's happening in the room where I am and the room where you are. Instead of many millions of collisions each second, here you could have collisions every day, every year, every century, depending on what molecules you're talking about. So it's very, very different from what's in the laboratory. Okay, so what does a dust particle look like? We can't take a picture of a dust particle that's very, very far away, astronomically speaking. So this is called an interplanetary dust particle. And interplanetary dust particles are a little bigger than the interstellar ones. The ones in clouds, for example, are typically a tenth of a micron in size. And these are 10 to 100 times bigger, but they show you the objects are obviously complex. And if you actually can take some sort of measurement of what the species are, they're mostly made of either carbon or silicon or both. So not very different, say, from the surface of the Earth. And dust particles are sometimes called grains. I don't know why. All right, so here is a much less detailed picture of an interstellar grain showing that there are different phases of it. The center of it is called the core, and that's typically carbon or silicates, depending on what star it was blown out of a long time ago to go into the interstellar medium. All right, the next phase outward is called a mantle, and in cold clouds, these mantles are composed of ice. Water ice is very important. Carbon dioxide and other types of carbon ices are also important, as are bigger molecules stuck in this mantle. And finally, on the outside, there is a surface. And of course, the grain is in a gas. And so we have to count the external gas as well. Finally, in this picture, you see what are called cosmic rays. These are high energy protons for millions of electron volts, and they can go right through easily the whole dust particle, and indeed cause chemistry to happen in the dust, as we will see later. All right. Now, here is a very simple-minded picture of what happens to stars. And the basic idea is that stars go through a sort of a phase, or many phases, and come back to where they started. And they go through clouds. So a typical star eventually comes apart and becomes clouds. The clouds come together and the material comes together, heats up to form new stars. So let's start here at the stellar system. That's like the solar system, and that starts in the lower right-hand corner. Don't worry about the arrow. I've cut off something about comets hitting the Earth. In any case, from the solar system, eventually the star in its center gets very old, about 5 billion years old, and starts to lose mass. And if we go to the next object, that's called mass loss. And what is it? It's losing gas and dust. Okay, so gas and dust comes out, and some of it comes together into what we call diffuse clouds. These clouds are actually partially transparent, and you can see through them, which means if there's some light behind them, you could actually do a standard laboratory type spectrum. Okay, and some small molecules are seen in this way. But the diffuse clouds don't last forever. Gravity collapses them, and eventually they make these dark clouds that I showed you actual pictures of, in which the dark color comes from the dust, but there's also a lot of gas. Okay? And these have temperatures, as I showed you for the TMC1, at about 10 Kelvin. So there are molecules here in this source. It's very full of molecules, as we'll see. But these dark clouds, most of them collapse. Now, as they collapse, the temperature, instead of getting lower, begins to get hotter. The collapse happens and gets hotter because material and radiation can't get out. So this is well known in physical chemistry that it will heat up under such circumstances. And what happens to the individual dark clouds is they begin to form in their center protostars that are protostars in the act of forming, although it's not quite hot enough to be a real star. And going around it, instead of calling things cold cores, we call them hot cores. They get up to 300 Kelvin, and eventually a star can be formed. But here we see what happens First, this picture that says giant cloud. Many of the clouds have many more than one star that have already been formed, and more stars are being formed as we look at them. So they are much more complicated than one simple dark cloud. The closest giant cloud to us is the Orion Nebula, which one can normally see much of the year. It's very bright. Nebula, by the way, is an old-fashioned word for a dense cloud. Anyway, so out of these clouds being formed in this giant cloud, we get a flattening as long as there's some angular momentum. And instead of having just these hot cores surrounding protostars, the protostar becomes a star. The dense gas and dust in the hot cores actually becomes planets. Okay, so we eventually have here what's called an accretion disk, in which we don't yet have planets. We have large dust particles surrounding, and now a real star, and rotating around in a flat plane. This is called either an accretion disk or a protoplanetary disk, and eventually forms a stellar system. Now, each of these sources has different chemistry, so chemistry has told us a lot about what we're looking at here. Okay, so here is this is not just my diagram, here's an actual picture of protoplanetary disks that have come out of the Orion Nebula. You see that in the middle there are stars, and surrounding the stars is a lot of dense dust and gas, and that again has the standard black color. Eventually, that will turn into planets as well, and then you will have real planets here, not just a star surrounded by dense dust. All right, now we're going to do molecules, and since this is also a history lesson, I'm going to put in years, and we're starting in 1919, and we're going to end in the current year. All right, so starting in 1919, this is now an interesting spectrum. Now, this has nothing to do with the interstellar medium. This has to do with stars. So if you look at our sun, and you're careful to do it, and you have a prism or a grating, you'll see the light is split into colors. You're actually seeing light from the sun, but the colors, the red, the green, and the blue, are blocked in certain wavelengths. And these are called the diffuse interstellar band. So every time you see one of these white lines or dark lines, the white lines, I think, are absorption, and the dark lines are, the white lines may be emission, and the dark lines are absorption. What are these things? Well, they were first detected in 1919 by a woman astronomer, Mary Lee Hager. And up to now, up to very recently, not one of them was assigned to a molecule or an atom or anything. Now, one or two of these 500 odd, what we call lines in spectroscopy, one or two of them have been assigned to molecules. How do you assign them? You do a spectrum in the laboratory and make sure it's the same as the spectrum from space. And you need more than one spectral line to make this believable. So still, most of these diffuse interstellar bands have not been assigned. We don't know what they are. And it will be exciting when some astronomer or astrochemist can figure out what they really are. Now we're going to skip to the year, it says by the year 1950, although these three molecules had been seen by then in space. They are very strange molecules. If you know some chemistry, you think, gee, how could these molecules exist by themselves? But they do in space. And these were found in the 1930s to 1940s. And the experiment was a electronic spectroscopy. That means in the visible. So you have a star, and the star from the light is going into, the starlight goes into a diffuse cloud. Much of it goes through the cloud, but some of it is actually absorbed. And from the absorption frequencies or wavelengths and also laboratory work, the molecules were assigned. Okay. And this to the right is the actual telescope that was used in those days to make a photographic plate, and the photographic plate was then looked at carefully. This was at Yerkes Laboratory near the border of the United States and Canada. And still standing. All right. Now, nothing much happened until radio astronomy became big. So this happened in the year 1968. And radio telescopes of that era had been around since the 1930s, and people began to see spectra in the radio frequencies. And that's also, if you can think of it as just like a radio, you turn a dial and you listen to channels. Here you turn a dial and you see spectra, and you know what the molecules are. So 1968 was the first. It was ammonia. It was seen by a Nobel laureate for lasers, and that was Charles Townes. And other molecules were in different clouds. So if you see something is SGR-B2 or Orion or W49, those are all of giant molecular clouds, have lots of different molecules. But I've just written down water. It was one of the first seen. Another one is formaldehyde. That's two hydrogens, a carbon, and an oxygen. And the ubiquitous in English means that it's seen everywhere. And 1970 was the simple diatomic molecule CO, Orion, and then there was something that was unknown. It was two spectral lines. It was the molecule was called exogen. That means it's not known. Okay, it was just a joke, and eventually it was seen in the laboratory. And this is a molecular ion. They're very unusual in the laboratory, but you can make them in a discharge, or you can see them in space. So this is called the formal ion, HCO+, the first ion to be seen. And what this ion is, there's a plus charge because it has one electron too few. And then there is methanol, one of my favorite molecules. I spent a lot of time studying it in the laboratory. And it was seen in space in 1970 by in a radio. What astronomers call a radio often means microwave or millimeter wave spectrum. Now, molecular hydrogen is probably the most important. It's certainly the most abundant molecule. It was seen, though, in electronic spectroscopy, not in the radio. For a molecule to be seen in the radio has to have a dipole moment. So there has to be a plus charge and a minus charge, and molecular hydrogen fails that, but it can be seen in electronic spectroscopy. All right. So some pictures of telescopes, okay? So this is the Nobayama radio telescope. It operated in Japan starting in 1982. So one of the first of the big ones. It's easier to make them, for example, than making much more smooth visible telescopes with glass. So this material you can make much bigger out of and collect as many radio waves as you can. It's hard to collect them, which is why they make such big dishes. So anyway, from space, the radio waves can come, and they come all the way to the ground. So this is a ground-based telescope. You don't need it in space. And the radio waves then bounce off the big dish and go to the upper little part. And from there, they go into a hole in the bottom. And then they have what's called the radio spectrometer, or just like a radio. I mean, you see the different frequencies. And then if they coincide with frequencies in the laboratory, you know what you're seeing. And laboratory experiments for even the most exotic molecules are now done. All right, so here is what you see, aiming the Nobayama telescope, aiming it at this TMC1, which I now showed you several times. It's one of these cold cores, and it is a radio spectrum, so it's in the gigahertz. It's not AM or FM, but it's in that frequency range, and you're seeing spectra. Okay, now the spectra, all of these lines have been assigned. And the assignments you could see up with the red vertical lines. The red vertical lines you see to the most right there's a very strange molecule CCS, okay, which doesn't really exist for very long in the laboratory, but spectroscopists have seen it. Now, what do you learn from such a spectrum? Well, every molecule has its own rotational spectrum, and that tells us it's a moment of inertia, up to 3 moments of inertia, and that tells us pretty much what the molecule is. So radio waves, besides being easy to detect from the ground, tell us a lot of information. They tell us also the temperature. Okay? They tell us the frequencies, of course. They tell us what the concentration is. Actually, the lines that are taller here show a molecule with a bigger concentration in that frequency. Every molecule has many frequencies, so it's rather complicated, but you can get the concentration. You can get the temperature by getting the intensity of different lines. And finally, you could get the Doppler effect. The Doppler effect means the whole cloud is moving with respect to the Earth, and you can get information from that. So you get a lot of information from a radio spectrum. Now let's go to the infrared. Okay. Now the infrared. Okay. The infrared radiation in some of it can't make it to the ground. And the basic problem is what's shown here, clouds. Clouds are full of little water vapor, little droplets of water, and infrarays get blocked by that. So the simplest experiment you can do without putting something into space is just use an airplane and put a telescope, which here is shown at least the door in the middle where the telescope would come out. And this it can be called a telescope. It's an infrared telescope. It works in the infrared. It's a joint project of NASA in the U.S. and the German equivalent. And so you can see a lot of infrared radiation above the clouds, the dense clouds, not all of it, because some of it is still in rather diffuse clouds that blocks it. On the other hand, the big advantage of a telescope is it can land every day. And with the years, as technology improves, you can put in better technology. On the other hand, if you're going to put something into space, it's very hard to do much with it. So this is another infrared. This is newer than by a few years than the so-called SOFIA. This is called the Herschel Space Observatory. Herschel was a famous astronomer, and this also works in the infrared, but in the so-called far infrared, which is very hard to do from the ground. Far infrared means it's closer to microwaves or radio waves than it is to visible. If it's close to visible, we call it the near infrared. And if it's in between, we call it the mid infrared. Anyway, so this has to get put into space, okay? Because if anything lower than that, it's going to be blocked in the infrared you're looking at. So it looks like a telescope. Of course, it's at an angle here, but you see the big dish, and you see it bounces off the light. The radio waves, or the far infrared waves, bounce off that and eventually go into a detector. Okay. The problem is this has to be cooled to liquid nitrogen temperatures, and there can't be dust around it. So it is not in orbit around the Earth. It is too dusty around the Earth, too wet, and so it is actually put in orbit around the sun. And indeed, most of the newer space telescope spectrometers are put in orbit around the sun just to get a cleaner system. So this telescope lasted for 5 years before they ran out of liquid nitrogen or liquid helium to keep the thing cool enough to actually take an infrared spectrum, and is now kaput. So we no longer have it. But what we do have is we have more stuff, and these now are interferometers. Now, you could, of course, build an interferometer in space. It's a hard thing to do. So most of the interferometers we see are visible interferometers, okay? Well, I'm sure, I don't mean visible. I mean, you could see it because they're on the ground. So they're ground-based. The biggest one is ALMA. which stands for where it is in Chile, and it means also that it's working in the millimeter wave. So, anyway, take a look at it. So there are quite a few of these things. They can give you a very, very bright signal because there are lots of. It's easier to have lots of little ones than one big one, especially when you have to cart them up the mountain so that you have better seeing. And this works in the millimeter, the radio, and even the submillimeter radiation. Okay, so what do you do with it? Well, an interferometer has several important things it can do. One thing is it can get you very high spatial resolution. You can look and see stars spread out, which you couldn't see unless you had one very big telescope. You put the telescopes closer together, and they all can move, by the way. Then you get higher intensity. So you can see, another way of saying that is you can see farther and farther away. Okay? Now, that is used very often nowadays, and it's hard to get time on it. You have to write a proposal and have to have a large group of people. Okay. Now, a similar telescope, but not quite as big in number, is called the Very Large Array, and it's actually being improved, and that works in the microwave, and that is in the desert of Arizona in the U.S. All right, finally, the last telescope to show you, okay, is the James Webb Space Telescope, and it just went up in November of last year. Again, it's one of these telescopes that's in orbit around the sun, and you can see it looks like a standard telescope, except here we have infrared radiation hitting the surface, bouncing up on top, and then coming through, and again with some sort of spectrometer device. And we're beginning to see the first pictures from it. All right, so all of these telescopes and all of the different types of clouds mean a lot of different molecules have been seen. And the number so far is about 250 molecules. I used to have a slide in which I tried to show all of these molecules, and I don't do it anymore. The simpler way of doing it, the better way, I think, is just to divide some of the more important molecules into classes and just go through them briefly. So the first class molecules are simple, so they're small is another way of saying it. Mostly diatomics or triatomics, except for ammonia on the far right. So we've seen H2 and CO, a lot of water. This is now in the gas. There's also stuff in the ice on the bottom here. We'll get to that. One of the smallest, anyway, polyatomic ion is H3 plus. Okay? So it's H3 is not it can't be seen. It's not a molecule, but you take away one electron and you can see it. There's a lot of deuterium in space too, so not only H3 plus, but also H2D plus. There are isomers, so not only HCN, but HNC, okay, and ammonia. All right, then the next two classes are important because there are lots of molecules in each class. One is exotic and one is very boring, or very simple in a sense to understand because they're all in the laboratory. Carbon chains are very exotic. Most chemists looking at these molecules would say totally impossible. But you can actually see them briefly in a spectrometer and a discharge, so you know where to look and you can find them in space. They can be neutral, positively charged, negatively charged. It's really crazy. And they can get up to about 15 atoms. Okay. Now, these are typically found in the 10 Kelvin regions, these dark clouds. In particular, the most popular one that's reasonably close is this TMC1. So here we see these very unusual carbon chains, which we think we understand actually how they're made. The next class are called complex organic molecules. They're not really complex, but we call them that. These molecules have more hydrogen than the carbon chains. Another strange thing about the carbon chains is the lack of hydrogen. These molecules in red are standard, as I said, in the laboratory, so they're rather boring. But they're not boring to astronomers for two reasons. One, because they may be on the way to making pre-biological material. There's a lot of thinking going into this. The other thing that's interesting to astronomers is that these COMs are very, they are not very rigid. So they have internal motion. And that makes the people who are interested in the quantum mechanics, it's very hard to understand their spectrum. And that is pretty much what I did as a thesis. So I still remember it fondly. Okay. Now, these were first seen in hot cores up to 300 Kelvin. And so people tried to measure them and tried to figure out how they could form at high temperatures. Except about 10 years ago, that they started being seen at low temperatures, middle temperatures, all sorts of temperatures. So now it comes that are almost everywhere, and we don't fully understand why. Other species, we'll go over more quickly. Inorganic species, okay, these are molecules that don't have much in the way of carbon. Fullerenes are interesting. Buckminster fullerene C60 looks like a football. European or Asian football, and C60 plus is one electron removed, and C70 is also like a football, but not a spherical. So these molecules have been found in space after they were found in the spectra were found in the laboratory. Then we have molecules called polycyclic aromatic hydrocarbons, which are multiple benzene rings. Benzene rings are just hexagons with lots of carbon and hydrogen. I'll show you pictures of those later. Ices. Okay, what can you see in the ices? Ices are much harder to assign because they have much broader spectra, but the smallest ones are CO and CO2. The most abundant one in ices in cold regions is water ice. In fact, there's almost as much water ice as there is any other molecule. The biggest one seen is methanol. So methanol, CH3OH, is seen both in the gas and on dust particles. All right. Dust particles, the chemistry is complicated. You have to worry also that dust particles can evaporate and become gas. That's called adsorption. I'm sorry, that's called desorption. And adsorption is when the gas sticks to dust particles. Okay. We have both of them occurring. All right. So now what do we do, or I do for a living? For the most part is to do what are called chemical simulations. Okay? And that is we write down lots of chemical reactions, such as people do, say, when they're studying our own atmosphere. And we solve them using some of the laws of chemistry. And that is, we put in all the reactions we can think of, and all the molecules in the gas and on the surfaces, they react with each other. And from that, you can calculate as a function of time and density, the concentration of every molecule you see and the spectra. So we can actually theoretically reproduce the spectra that I've been showing you. Now, once we have such information, we can learn about physical conditions of the sources. And we can learn about how old they are and what their history is. So we learn an awful lot, both from spectroscopy, that is observations with the telescopes and spectrometers, and also by understanding the chemistry and the reactions that happen to make these molecules. So we have a history now of different types of reactions. The first, an important one, is how molecular hydrogen is formed on grains. The ones in black are reactions between ions and neutral species. Okay, well, I'll show you that. On the bottom, these are neutral and neutral species. This is, again, in the gas, it's black. And you have to have one reactive species. If you have two species that are not reactive, there's always a barrier in chemistry. And that means, especially at low temperature, you don't see anything. So you need one radical and one neutral. And then there is a very complicated grain chemistry occurring on cold grains. And the numbers here are the years in which they were found. So for in which they were actually written about and understood, and then found. And so 1971 H2, and really up to the present, molecules like radicals versus neutrals, or grains. But they started in the years that I'm showing you. All right, here's the formation of hydrogen. It's very simple. Two hydrogens cannot come together in the gas. Why don't they come together? They hit each other and come apart. There's nothing sticking them. They don't have glue, right? On the other hand, they can stick to a dust particle, because dust particle can absorb a lot of energy from hydrogen atoms, and they stick. The hydrogen atoms then can move around because they're bound very loosely at low temperatures, and make molecular hydrogen, and with it has enough energy to come off. This works from about 10 to 30 Kelvin. Lower temperatures, the hydrogen atoms don't move, and at higher temperatures, they come off before they can move. So it's only produced, according to theory and experiment, in a narrow region of temperature. Here is a much more complicated series of reactions. These reactions involve ions and neutrals, and I'm showing how water and OH, a radical, can be formed in the gas. What happens is it starts with molecular hydrogen, which gets bopped by one of these high-energy cosmic rays, and an electron comes off to make H2 plus, an ion of hydrogen. H2 plus reacts with H2, makes H3 plus, and H3 plus can react with oxygen, and eventually one comes up with an ion, H3O plus, that reacts with electrons, becomes neutrals, and the neutrals tend, if you go to bigger ones, they tend to be the carbon chains. So carbon chains are made by such a synthesis. So we understand we need ions and neutrals, and the ions eventually come apart with reactions with electrons. So anyway, so here on the other hand is we have reactions on a surface. So here's what a surface looks like. It's not smooth. It has wells and barriers. And molecules come down, or atoms come down and stick on wells, and then move a little by hopping over barriers or tunneling through barriers. And if they come together, they can react. Okay. We know something anyway about the size of the barriers and the energies needed to get everything off the grains. So this was first studied by two scientists, Langmuir and Hinchelwood. Okay, so here's a simpler picture. Without showing tunneling and wells, it shows various species sticking to a grain and coming together and reacting by giving off energy. So, for example, if oxygen comes down and hydrogen comes down and then another hydrogen comes down, you can make water. If two hydrogens are together, you can make H2, and you can make methanol, you can make CO. And water, other than hydrogen, is most abundant, and it's in monolayers, which surface physicists use as a unit, up to 100 monolayers. All right. And at low temperatures, only the lighter species move. At higher temperatures, all the species move around and eventually come off as the temperature gets higher and higher. All right, so here is a very complicated picture, which we're only going to go through very briefly, and that is what happens during the star formation business, in which you start with a cold core and you end up with a star forming surrounded by a hot core. The chemistry is rather complicated. It consists of both gas phase and surface chemistry, and eventually something like high temperature to kick off the molecules into the gas, because most of these molecules we see here are these COMs, and that's why people used to think they were only formed at high temperature. Then we learned that they were also formed at low temperature, and then we learned that this is not the whole story here. We have to wonder how they could be formed at low temperature as well. But this idea that it was formed at a higher temperature in a warming system was done in 2008 by myself and a graduate student. So it lasted for a while, but not any longer, because one of the things that's wrong about it, it can't do it. It can't work for in a cold climate. It only works as it warms up. Turns out. So if you see lots of these cobs in the cold in a cold region, either on the gas or on grains, you need another theory. All right. Some recent work, which we'll take this to the close here. First, I want to show you these so-called aromatic or polycyclic aromatic species of benzene rings, actually seen in spectra very recently. Then something called radiolysis, that's bombardment by cosmic rays, and then showing you something that can actually work to make big molecules at low temperature. All right, so here is a picture. This is this TAURUS. TAURUS, by the way, is this picture is much bigger than TAURUS. TAURUS is actually a long line, and it's put in the color here. There's no color; it's black. But anyway, and these molecules you see are all in the orange part of it. They're seen, and this is what's meant by these cyclic polycyclic species. Now, the first one was seen by rotational spectroscopy. The telescope used is a telescope called the Green Bank Telescope, which is actually close to my university. And it is rather big, even though it's a single telescope. And that was enough to do rotational spectra to actually determine one molecule from another. Okay. So, all right, that was done by a large group called GOTHAM. All right, now radiolysis. This was done by our group. It's also very common to see this sort of thing done in the laboratory. Basic idea in the laboratory is you start off with an ice, and you want to start off with an ice that has some carbon. And that you can imagine it's on a grain if you wish. You could just imagine it's a block of stuff if you wish. Cosmic rays hit it, okay? And what happens is they make ions and electrons, and the ions react and the electrons react, and they go off in all directions. And this is what you would see in the laboratory. Actually, this was theory. This was from a postdoc of mine, Chris Shingeldeck, actually doing a very complicated calculation, getting this random structure. And many of these molecules now are the so-called complex organic molecules with enough energy to come out. By the way, the cosmic rays, unlike just simple radiation, can actually go through the grain completely, so making these molecules and ions and electrons. So it's very complicated, but it's measured. Many laboratories have shown that this actually happens. So presumably it actually happens in space as well. Okay? And this is actually at low temperature that we see it. All right, here we have, I think this is the last process to see, this is non-diffusive surface reactions. So these are reactions that, at least partially, do not have to do diffusion. By diffusion is meant that picture I showed you with the barriers and the wells. That has atoms and molecules moving around over a whole grain. So that's called diffusion. If the molecules and atoms on the surface are not moving, some part of the process is not moving, it's called non-diffusive. And this appears to explain why COMs, the COMs, can be abundant at low temperature. So here's a much more simple picture showing the formation of carbon dioxide. The lower one and the upper one. The upper one is simple. A carbon monoxide and an oxygen come together on a surface and make CO2. That's very slow because it has a barrier. Okay. So here we have the other method, which is fast. So we have a hydrogen and an oxygen coming together. It's at low temperature, so they move slowly, and they form OH. Okay? But OH can see lots of carbon monoxide molecules. There are lots of carbon monoxide molecules around. So an OH, as soon as it's formed, is right next to a CO. It doesn't have to move at all. And they come together and quickly make CO2 plus H. And without that reaction, we were not able to make enough CO2. We never understood it. So this is very important for making bigger molecules at low temperatures. So with this non-diffusive, we can explain these bigger molecules both at low temperature and at higher temperature by a regular diffusion. So now we begin to understand where the comms are made, why they're made over such different regions. And I end with the standard acknowledgments. These are to students, many, well, at least half of them have now graduated, and the remainders are shown here. And the money that comes from the National Science Foundation and NASA. And of course, the students are the ones who did much of the work. So thank you very much. And if you have questions, I'd be happy to answer them.
Yes, sir. Thank you. That was indeed a very interesting lecture. And Samruddh can we have a lot of questions from various sources. And
Yeah, I have a question. Can I ask?
yeah.
Yes, so basically from all these spectroscopic methods, can we calculate can we determine the presence of the molecules, or we can also calculate their mole fractions or the mole ratios?
Yes, you can get the concentrations from the spectrum.
So sir, can you tell us a
just
bit
like
how
we're
it's
doing
done?
electron.
What, sir? Can you repeat it?
I'm sorry?
So can you repeat again? Your voice was a bit shaky there.
No, sorry, I'm not being able to hear very well.
Sir, can you repeat again? Your voice was a bit
Slower.
Yeah. So can you repeat again what you said?
What did I say?
Yes,
But
sir.
I didn't quite understand the question, so we need to repeat the question first.
Oh, okay. Sure, sir. So basically, from the spectroscopic methods, can we calculate only the presence of the compounds or molecules, or can we also calculate the mole ratios or the mole fractions?
Yes, certainly. We do it in two ways. I mean, one, you can measure them from the spectra, and two, you can calculate them with quantum mechanics, or you do these simulations. Sometimes called molecular dynamics. I mean, we do calculate everything we can do using theory, and we try to make. And the theory also has in it how old the clouds are, because older clouds will have different chemistry than younger clouds. These dark clouds I showed you, they last a million years. So it's so things can change then.
Oh, so actually, sir. Yes, sir. Go ahead.
No, what I want to say is that spectroscopy is the same in space as it is in the laboratory. So all the same techniques, just slightly different. What's if different? Many of the molecules are unusual. Two, the concentrations are very low, but these sources are huge. I didn't mention how big these sources are. So if you multiply the size by the low density, you get about the same type of intensity in the spectra that you would get in the laboratory. So it is not weak, even though you don't have a high density, because the clouds are so big.
Oh, sir, that's great. So, I have another question. So, basically, we are trying to simulate chemical reactions for the atmosphere of Titan, and we are using the INMS data. So that's ion and neutrals mass spectro.
That's correct. Titan is the closest to an interstellar cloud.
Yes, sir.
Most of the planets are not. The Earth, for example, is very poor in exotic molecules. So often people who do astrochemistry in space also study Titan. And the chemistry is very similar to the ion molecule chemistry, but the densities are higher, so it's not exactly the same thing. If you go into the higher atmospheres of Titan, it becomes less dense and more like an interstellar cloud. Lower down, it's still interesting and it's still somewhat similar in chemistry, but it is much denser. So it's not exactly the same.
So, sir, if we want to simulate those chemical reactions, what all like will we have to keep in mind? Like, what all variables do we have to consider to make the model?
To make the model. Well, that's a very this has been done historically. We started
Oh,
off with a very small number of molecules that we knew were measured. This was in the early 1970s, and people had still been studying iron and neutral molecules. Neutral iron neutral reactions had been studied, and that was the first important type of reaction that was put into models. I had written down the years. Some of the more obvious ones took a long time. So to get neutral reactions, I mean, most neutral reactions at low temperature in the gas have barriers. So you couldn't put those in. And we didn't put grain chemistry in until the 1990s. I mean, so it took a long time.
oh,
So
so
a lot of
basically,
people working.
it
It
gets
wasn't one
very
person.
complex.
I'm sorry. It's very
So basically,
complex.
through the time it got very complex when we got to know more stuff.
That's right. You have that too, right? Yeah.
Okay, sir.
So
Thank you.
we're trying to write a history of this, but there's so much history. It's very hard to do. So we're trying to. It's a large group trying to put together something called the Handbook of Astrochemistry to answer questions like this and how it changed with time.
Oh, that's great, sir.
Well, it'll be a while, but yes,
Thank you, sir.
you're welcome.
Uh, so with that, I do. Are there any other questions, sir? So with that, it is the wrap of the questions too. Uh, it was a very enlightening lecture. Enlightening lecture. Thank you once again, sir. On behalf of Said Celeste, I would like to once again thank you for devoting your time to educate and enlighten us on such an interesting field and topic.
Oh, thank you for listening.
Thank you, sir. Thank you. Thanks a lot.